Take two.
I'd like to welcome Peter for our next session on the solar-powered Apple II. If you heard an earlier pitch for this session, we're going to have a field trip component. He's going to bring his actual mobile rig with us, but I'm sure he'll tell us about it. Thank you, Peter.
Thank you, Andy. Yeah, this afternoon I'm going to talk about solar power in general, specifically how to solar power an Apple II. The same ideas apply to anything that you want to solar power. As far as solar powering an Apple II, one of the advantages is you can get scenery like this. I took this picture the day before KansasFest started, parked in the National Forest overlooking the Grand Tetons in southwestern Wyoming. So why bother with solar power? The obvious first benefit is it's useful when utility power is not available, and that's, as I'll explain more in a moment, that's the biggest motivation for me. It can also help reduce the costs of utility power. You do need to look at the cost of the solar system itself. There's usually substantial costs associated with that, and it takes a number of years of owning the system before it pays off. So you need to take a look at that trade-off. Also, it reduces dependency on utility power. In many places, the utilities just aren't very reliable. And lastly, solar can reduce environmental impact. But as I was saying, the motivation for me was that it reduces dependency, or eliminates dependency on utility power. Shortly after KansasFest last year, I sold my house in Oklahoma and moved into this van, and I'm traveling full-time and doing that for about 5 months. The obvious problem with the van is extension cords aren't long enough. So not only do I need power for day-to-day things like lights, but I also telecommute out of the van. I need power for computers, power for internet. I have a satellite internet dish as well, and it's pretty important that the power is reliable, because if it's not, then I can't work, and then I can't afford the van, and it just goes downhill from there. So this is a picture I took, I think it was about 2 weeks ago, in the Caribou National Forest in Idaho. This 2C is running in the picture. You can't see it because it's washed out a bit, and also because of the CRT refresh. But it's running entirely off of solar power. I have 900 amp hours of batteries stored under the rear of the van, typically where the spare tire goes. And I also have 600 watts of solar panels up top. Here's a better picture that shows the solar panels, 3 200-watt panels up there.
We need that connected to the car.
Pardon?
I guess there's no electrical engine in the car anyway.
No, it's a gasoline engine with a typical starter battery in there, an isolated electrical system with batteries, solar panels supporting electronics. I do have the ability to cross-connect the system, so I can charge my battery bank off the alternator. I have never needed to do that unless I park in the shade for several days.
And how many watts was your solar? 600 watts?
I have 600 watts of solar, yes. So far it's done a pretty good job of taking care of everything. We'll see how it works in the winter. I'll talk a bit more about solar radiation changes throughout the season and so on. But
you may find it's better in the winter because the panels are colder.
Yeah, that is a trade-off. Less sun, but when it's colder, better panel performance.
What brand panels are you using?
I'm using panels from Sanyo. I'm using these particular panels because they're just the right dimensions to fit on top of the vehicle. It's like a jigsaw puzzle. And many of the newest, most efficient panels are very large. They're ideal for putting on the top of your house, but yeah, my house has a funny shaped roof.
You have security problems. I mean, unless you're with your vehicle all the time, you have to have it in a secure place.
Well,
I mean, those panels to begin with are probably worth something. People probably know it.
But the panels are 10 feet up, so it takes a bit of effort to get to. It's not something that you can just walk off with quickly. These are the major parts of a solar system. I'll go over them briefly so we're all talking about the same thing. Obviously, at the top of the diagram is a solar array. It takes the energy from the sun, converts it to electrical energy. The power from the solar array varies depending on a lot of factors. Depending on the manufacturer, the model, the particular manufacturing lot, depending on temperature, depending on the amount of sun, depending on the age of the panels, you can get significantly different voltage out of the array. For small solar systems, you can simply connect your devices directly to the solar panel. However, for all but the smallest systems, that's not really practical. It's much easier to pick a common voltage, such as 12 volts, design all of your electronics to run off of 12 volts, and then use a charge controller to convert the power from the to convert the voltage from the solar array into a typically voltage regulated supply. The charge controller also provides other functions. Most batteries to be fully charged have a 2 or 3 stage charging profile, where each stage of the profile has specific voltage and current limits, and the charge controller will provide that. So the charge controller is usually more than just a voltage regulator. Another interesting bit is the voltage current curve for a solar panel is not linear. So there's a very particular point on that curve that the panels need to operate at to get the maximum power out of it. And there's charge controllers called maximum power point tracking controllers, or MPPT, that will analyze the panel, find the maximum point on the curve, and operate the panels at that. There are 2 basic types of solar systems. The first type is called an on-grid, where there's also a connection to typical utility power. The advantage of that is when you don't have enough solar power, you simply get it from the utility. When it's dark out, if you didn't store it in a battery, no big deal. You have an alternative power source. You can design your solar array for the typical case, but say when you turn your washing machine on, you don't have enough solar power, no big deal. You can design the system to automatically switch over to power from the utility. In my case, however, I have a battery. The other type of system, which is what I have, is called off-grid, no utility connection. In that case, you almost always have a battery bank as well to store power for when the solar power isn't available. I also have a battery charger such that I can plug in if I need to and charge the batteries, but I've never needed to do that.
This is a battery part of the solar system.
Right.
Apart from the car's battery, right?
Correct. I have a separate battery bank. I have about 900 amp hours of absorbed glass mat batteries where the spare tire would normally go.
How much, if you don't mind me asking, how much did you spend for the panels and the batteries and so forth?
I don't know those numbers offhand.
If somebody wanted to recreate what you did, the kind of investment potentially they'd be looking at?
I would have to go look those numbers up. It's on the order of thousands of dollars.
Sure. Thanks.
You can run your appliances, your computers, your lights, your refrigerator directly off the DC power from the battery. It's often convenient though to use something called an inverter that converts the typically lower voltage DC from the battery into 120 volts AC or 220 volts AC, so that you can plug your familiar appliances directly into an outlet. Disadvantage with an inverter is they're a bit inefficient. The most efficient inverters are maybe about 92%, so you're tossing 8% of the power out the window. The less expensive inverters can be much, much worse than that. You're talking 60% efficient. Watch out for inverters that don't tell you the efficiency. So the first step in designing a solar system is to figure out how much power do I need. And I'll walk through an example figuring out the power required for an Apple IIc, and a 9-inch Apple monochrome monitor, which is the computer that you saw earlier. Once we've figured out how much power we need, we can look at estimating the battery bank size, the solar array size that we need to match that. So here's another picture of me using a solar-powered Apple II. It actually is powered on, but of course you can't see it here. And this is another angle from the picture that I showed earlier.
How does that screen work outdoors?
Not very well. It's just not bright enough with it being backlit. I can read it, but it's. I would want to. If I wasn't posing for a picture, I'd put the computer in the shade. Here are the maximum power requirements stated from Apple for assorted Apple products. Every electrical product will state the maximum power requirement. On the Apple IIc, it's printed on the power brick right here on the bottom, and it says input 120 volts AC, 25 watts. Multiply those two together, definition of power, and that's how I get the number that you see here for the 2C. The computers with integrated power supply will typically have it printed on the bottom, or sometimes on the back where next to the power input. The manuals also specify, and this is the same not just for computers, but anything that you're plugging into the wall, somewhere will tell you the maximum. Keep in mind that this is the maximum. You will never actually draw the maximum power. No sensible engineer is going to design the device to draw the maximum power that the power supply is rated at. And power also varies quite a bit depending on what you're doing. For CRTs, it depends on what's being displayed, brightness. For computers, it depends on what the computer's doing. Depends on the peripheral cards in there, is your disk drive running, and so on. So the best way really is to measure.
I'm really surprised to see the GS has a much lower watt requirement than a 2E.
Yeah, I was too. This is based on the output power from the power supply in the technical manual. I did not actually look at a GS to see to make sure this matches what's printed. Since they were specifying the output power, the power supply has some inefficiency, so it's possible that the input power is a bit higher.
That's also just going to be the base GS, no memory card, no accelerator.
This is the maximum rating on the power supply. So the maximum it's going to draw, but what it's actually going to draw in your situation depends on, yes, your configuration, and it'll even vary as you're doing different things. So the best, yes?
Conversely, why does the Apple E take so much more power?
It's the maximum rating on the power supply.
Just because
You're allowing for more power they ever need.
They probably over-designed the power supply. I would never expect it. I would expect a GS to, in practice, draw more power than a 2E. I have not personally measured it, but this is what the power supply is rated to supply, not necessarily what the computer is drawing. I would recommend grabbing a multimeter or a watt meter, or there's a commercial product out there called a kilowatt that will measure the actual consumption for you. So I actually measured the draw from the 2C. The power brick alone, just the power brick, not plugged into the 2C, plugged into the wall, pulls 2 watts. The 9-inch monitor draws about 20 watts, and compare that to the maximum that we see back here, which was 36 watts. I measured the CPU alone at 12 watts, or around 12 watts. It varied quite a bit. And then I plugged in both the CPU and the monitor. It was the lowest I saw it go was about 31 watts. The maximum I saw it go when it was booting into, I think, the system utilities and the drive was spinning, was up around 40 watts. Obviously, that might go higher. Certainly go higher if you plug a second floppy in there.
That 12 watt typical for the CPU, is that inclusive of your power brick?
For that number, yes, it was the power brick plugged into the CPU, monitor turned off, unplugged rather. There was also a CSA2 post about a year ago. Several people posted numbers. I have not verified these numbers. The second and third numbers don't make sense to me because they exceed the maximum rating on the device. So it's on the internet, so I guess the message here is measure your own configuration, don't believe what other people say. Interesting tidbit though is that the System Saver 2E alone is pulling 7 watts. Don't know how they get a fan to pull 7 watts, but someone did. On the other end of the spectrum is the 2E main board, no memory card, no keyboard, nothing, just the motherboard was 4.2 watts. So quite a bit of variation. And the same thing is true with modern computers. Take some of the modern Core I processors, and if you look at the power consumption, they can go down from 15, 20 watts up to over 100 watts instantaneously. And they're designed that way, so they're more efficient and cooler. So the next step is to come up with an estimate of how much power we're going to need. I decided to use the maximum power ratings here. If I had more time, I would do a better job of measuring the power requirements for my typical use, but I didn't do that, so I went with the maximum to make sure I was definitely covering my requirements. Then I figure out how much I'm going to use the computer per day. I figured, well, 8 hours per day, of course, unless I'm at KFest, and then maybe it's around 20, but then power times the usage in hours gives us a measure of energy. Add that all up, get the number on the bottom right, and I figured to run the 2C and the 9-inch monitor for 8 hours a day was going to take me about 488 watt hours per day. Doing your estimates per day works for me, works well for me. It matches up with how the solar radiation is typically quoted, and we'll look at that in a little bit. You may want to do an average over a longer period of time. So again, we get another picture of a 2E with great scenery. So now we figured out how much power we need. The next step is to figure out the solar power that we need to provide the energy that I showed you earlier. The first step, and probably one of the more complicated ones, is to figure out how much solar radiation are we getting. And this varies depending on the time of year. It varies depending on the region of the country you're in, and the best resource I found is the National Renewable Energy Laboratory website, and let's go take a look at it. There's a couple of sources of data here, and I'll briefly go through those. We'll look at the solar radiation for Kansas City, and we'll use that for our system design in a moment. Over here, if we click on Launch Viewer, it takes us to a tool called PV Watts version 2. We can type in our address. And it thinks for a moment. And there we go. Now it gives us excellent historical data about Kansas City. It tells us that the annual average, we get 5.06 kilowatt hours of solar radiation per square meter of the Earth per day. This tool is targeted at on-grid solar installations, so it also gives us the average utility rate for electricity, and this helps us do a cost-benefit calculation for figuring out how much money are we going to save with solar power, is it worth it? Next, let's click on Send to PV Watts, and this takes us over to a tool called, I think this is PV Watts version 1, version 2. This can give us a little more detail. It pre-fills in the latitude and longitude, then we can give it the power rating on our solar system, measured in kilowatts. There's also an efficiency factor there, which I'll talk more about in a moment. We can tell it the type of array. Throughout the day, the sun moves across the sky. The solar panel produces the most power if it's pointed directly at the sun. The simplest type is a fixed tilt that doesn't move, where the solar panel doesn't move at all. There's one-axis tracking where the panel will move across the sky and track the sun. Two-axis where we'll also move or change in elevation to match the position of the sun throughout the year. We're just going to choose fixed tilt. I am going to type in 0 degrees, which is what I have since my panels are flat. And I'm just going to assume they're pointed directly south. Don't particularly care about the cost of electricity because I don't have any other choice, but it's useful information if you're looking to add it to a house. Click calculate. And we get a nice little chart that breaks down the average solar radiation by month. This can help you plan for different seasons, worst case. It also calculates the value of the energy that we're generating based on your local cost of power. I also want to show you one other link. This is an older source of data, also from the same organization. But for at least for me, I find this organization a bit more useful. This is also called the Red Book. Yeah, different Red Book. It's just a really long name. So let's see if I can zoom in so this is actually readable. That's sort of readable. This not only breaks out the solar radiation by month, it also gives us minimums and maximums. That's very useful for, again, planning for the worst case. I'm just going to go with average. But if you have if your Apple II is running your nuclear reactor, you need to plan for the worst case. So you're going to say, okay, what's the, I think, 29-year historical low for solar radiation? That's the number I'm going to plan for when I'm designing my system. For me, I'm just going with average because that's close enough. And if my power fails, it's not the end of the world. So take a note of this number over here, 4.3. We'll come back to that in a bit, but that's the average solar radiation for a solar panel mounted flat in Kansas City. Once we figure that out, we need to calculate what rating on our solar panels do we need to actually generate that much power. We take the energy estimate that we came up with earlier, divide it by what's called the equivalent solar hours, and then multiply that by an efficiency factor. And I'll talk about all those in a moment. The solar hours is an idea of, in a given day, how much energy are we getting measured compared to the ideal sun, which is, I think, I'm trying to remember what their standard is, but they have a standard for description of what's considered the ideal sun. I think it's a 25 degrees Celsius and 1,000 watts per square meter. It's called the standard test conditions, but the point is there's the concept of equivalent solar hours, and due to the way it's defined, it happens to be the exact same numeric value as the solar radiation values we saw earlier, kilowatt hours per square meter per day is numerically equal to the number of equivalent solar hours. Efficiency is another big thing that's often overlooked. There are a lot of things that suck up the power in your solar system. First, when you're buying a solar panel, they might tell you, oh, you're getting this 300 watt solar panel, but you look at the fine print and it's 300 watts minus 10% to 0%. So it's not quite what you hope for. Different brands do it differently. There are some brands that will advertise, say, 0 to plus 5%, and they usually advertise that prominently, and it's worth taking into account in your calculations because I'm sure they're not giving you the best performing panels. I'm sure they're giving you the worst panels they can that still meet the specs. Charge controller losses, the very best charge controllers and maybe lose 1 or 2%. Typically it's much more than that. Inverters, 8 to 30% more if it's a bad inverter. Take a look at the manuals for the inverters. If they don't tell you the efficiency, you probably don't buy it if you're concerned about efficiency. Battery losses, when you're charging a battery, you need to put more power into the battery than you took out. It depends on the type of battery. There are also losses in the wiring. It's more prominent when you're dealing with DC, particularly over distances. Say if you have your solar array in a field next to your house and you have a long run of DC wiring. Also, the angle that the sun is hitting the panels. We talked about solar panels that might track the sun. Temperature of the panel makes a big difference. Cold panels actually perform better than hot panels. There's dirt on the panel, shade on the panel. You get a few leaves shading a tiny corner of the panel, and the power output will go down disproportionately. And of course, age of the panels.
So how long do solar panels last then before they start to degrade significantly?
They start to degrade immediately, but the lifetimes that I've seen stated are on the order of 20 to 30 years.
Do they degrade straight line, or do they degrade subtly down, like level off, or do they go near the top for a long time and then fall off?
I do not know. There will be a link in the notes that show up when this is on the website that shows a research paper where they looked at failure modes of different panels and also the effects of age. I think it was on, if I recall, it was on the order of less than 1% degraded performance per year. I didn't look at whether it was linear or not. So let's plug our numbers in. We came up with our energy requirement estimate earlier, 488 watt hours per day, divided by the 4.3 equivalent solar hours per day that we got out of that Red Book document that I showed, times an efficiency factor. I've read different numbers for the efficiency estimate ranging from about 50% up to about 77% that you saw on the PV Watts website. I don't know what the I haven't measured this efficiency on my system. For this presentation, I'm going to go with 77% because that's what the PV Watts tool uses, and I figure they're probably more accurate with those things than I am. But think about it, research the particular components that you're using. A few percent difference can practically make a big difference. Yeah.
We had a solar conference in Lincoln a couple years ago, and the question was just this: what about efficiency? And I don't remember who the guy was or where he was from, but he said there was some chemical characteristic that kept the efficiency under 59%. And I'm sorry, I don't have the reference for that. But
yeah.
I think if you're getting 77%, that's probably pretty good.
There's two different types of efficiencies that we want to talk about. I'm talking about the conversion efficiency. We get power coming out of the solar panel. What do we lose before we actually get it to the device we're trying to power? There's also the efficiency of the solar panel. Typical consumer solar panels are about 15 to 18% efficient right now. So that means only 15 to 18% of the energy that hits the panel comes out the other end. there's certainly active research going on that improves that quite a bit, but as far as I can tell, those panels are basically unavailable to regular folks like us.
Work for NASA, maybe, get their quality.
Yeah, maybe. So plugging these numbers in, we get about 150 watts necessary to power our 2C and monitor. This is the minimum to break even. You may need to make a personal choice about, well, do I want to more than break even? Do I have other things to power? What am I going to do when there's clouds out? It's a tough balancing act. If the power is essential, you can keep throwing money at it until you have enough to take care of every situation, but you need to balance the cost versus how important the power is to you versus the alternatives that you have for getting power, such as generators or utilities. Yeah.
As the car runs, I guess it charges the car battery. And when that's completed, do you have a way of charging your solar system battery on the car?
I do. To date, I have never needed to use that function. But I do have that option, so that's my backup. Of course, there's problems with solar power. What happens when those nice clouds in the background decide to come and shade my solar panel? What happens when the sun sets? And for an off-grid system, the answer is, if you need power, you need to have a battery bank to store that power. So I'd like to talk briefly about sizing a battery bank. Again, this is a difficult choice. It depends on your requirements. Are you just using your Apple II to play choplifter, and if the power gets low, you turn it off? Are you using it to run your business, and if you turn it off, you start losing millions of dollars a day? What are your alternatives? Typically, when you're sizing a battery bank, you look at how many days of reserve do I want. If a giant storm rolls in and I don't get any power, how many days do I want to last before I have to go find an alternative or shut things off? You can also look at the historical data for solar radiation. You can look at the minimum, and that can give you a pretty good idea of what's going to be the worst case.
So what happens if your batteries are discharged less than 50%, or if they're fully discharged? Does that ruin their life, or?
Yeah, it depends on the battery chemistry, but lead acid batteries, if they're discharged more than about 50%, the lifespan of the battery starts to go down substantially. If you look in the battery manuals, and I'll have a link in what's posted, there's a curve showing the capacity and lifespan of the battery versus minimum discharge.
I bought some from Costco, and I realized even if I don't use these, they're probably going to be losing a little energy just sitting there. So I'm going to have to make sure to keep them charged up all the time so that I don't have that loss. So it becomes a weekly or monthly maintenance to keep them going.
Yeah, it does. You can get little trickle chargers that probably do that pretty well.
Charge controllers help with that too, so they don't overcharge your battery.
Intelligent battery chargers take care of that. They have a multi-stage charging algorithm that takes care of keeping the batteries charged. When they're fully charged, it drops down to a low current to keep them charged. So to figure out the size of battery bank we need, just going with the simple concept of number of days I want to last without solar power, take the energy estimate that we came up with earlier. Unfortunately, battery banks tend to be sized in amp hours, which is not a unit of energy, but that's how batteries are typically sized. So we have to divide by system voltage. In my system, it's rated at 12 volts. It's typically closer to 13 volts, but that's just how the systems are rated. If you have a 12-volt system, it is rarely 12 volts. It's typically around 13, 14 volts. Multiply it by, in my case, I'm going with 3 days of reserve. So if I have no solar power for 3 days, I want my battery bank to last that long. And then divide it by 50% to account for the minimum charge of the battery. And I get about 232 amp hours. And you can get a single battery that will meet that requirement. Something else to be aware of is some batteries are not designed to be deep discharged. So your car's starting battery would not make a good battery for a solar system because it's designed to provide high current for a short period of time to get your vehicle running. With a solar power system, the battery is discharged and recharged constantly, and a typical automotive battery will fail prematurely in that situation. So look at the ratings on your batteries and look for, usually marine batteries are rated for deeper discharge. So this is the result of a solar-powered Apple II. And this is the Apple IIc that's in the picture. I did not bring the monitor that goes with it. Again, designing a solar system is a bunch of trade-offs involved. You got to figure out what do you want, what do you need. Read the data sheets that come with the different components. Some of the manuals for, say, charge controllers are excellent. They talk about considerations for selecting the right charge controllers, sizing things appropriately. You need to think about the alternative sources of power that you might have. By far the biggest, the cheapest, yes?
Go ahead.
Okay.
When you're finished.
Okay. By far the cheapest thing you can do, though, is reduce the amount of power you need. Obvious thing looking at the power measurements that I have are the power requirements for the CRT. If you can, do without the CRT. Remove unused cards, peripherals. Don't build a machine like Tony. Tony had a picture that he posted a while back with, I don't even know how many hard drives and floppy drives he attached to the thing. But if you don't need something, put the card in the drawer, and if you need it, then plug it in later. We also looked at the efficiency of the inverter. That's a big thing that you can replace. James makes nice adapters that go inside most of the Apple II computers, and you can plug use that adapter to plug in a modern DC-DC converter. You can skip the inverter entirely, and a DC-DC converter is also more efficient than one that goes from AC to the DC that the computer needs internally. One nice thing about the 2C is this power brick converts AC to DC. It's a step-down transformer and a bridge. It puts out about 15 volts DC. But the computer itself will accept voltages from 9 to 20 volts DC. So if I had the right connector, I could connect this directly to my battery bank and skip the brick, skip the inverter.
And is there a reason why you haven't done that?
Yes, I don't have one of these DIN connectors. I had a special order and I waited too long. But the 2C technical manual gives you the pinout on that thing. It tells you the maximum power draw, everything you need. Yes?
Now, are you using a 2C in connection with the solar power system simply because you like it or interested in Apple computers? Or is it more or less efficient or draw more or less power than the current model computer?
The current model computers give you much better performance for the power. I think I measured this computer, and actually what we can do, somewhere here it'll tell me the power draw. There we go. Here we go. It's telling me that at the moment my computer is drawing about 20 watts from the battery. And it'll probably go down and unplug the projector. That takes a bit more. But if I start something processor intensive, it spikes up. So I get more performance by running more performance per watt of power with a modern computer, but obviously I'm here, so I like Apple IIs. I wanted to run an Apple II off of solar. Honestly, in most cases, I'll probably use an emulator because it's more convenient, but sometimes I want the real hardware.
Does it draw more watts than a current model computer?
The
It's
2C?
20 watts.
Yeah, it was around 20 watts.
So it's
So
about
it's-
14 at the moment.
So actually something like the 2C doesn't draw a whole lot of power.
So, even though, I mean, thinking, a current computer, you say, is more efficient per watt of power it
Mhm.
draws. Does it draw more watts, so that overall you wind up drawing more?
Usually not.
No.
It depends on the particular computer that you buy,
Okay.
but
So it's a matter of comparing particular computers. not
yeah.
differentiating between vintage and current.
Yes, laptops do a pretty good job of minimizing power, and because they've got to run off a tiny battery. If you get your giant gaming desktop, I would expect the Apple, say a 2C or any Apple II to draw less power. And the last thing you can do to reduce power requirements is, turn off the Apple II and go kayaking or something like that.
What does my backyard look like?
Yeah, where was that taken?
This was taken in Grand Teton National Forest on Lee Lake, looking at the, Grand Teton National Park in Lee Lake, looking, I think that would have been west towards the mountains.
Peter's backyard looks much better than most of ours.
It's because I can move my house to the backyard.
Get a bigger kayak so you can take your Apple II with.
Oh, and hope I don't flip.
See the shot there, you're sitting at the computer. But the earlier shot, there was the van and nobody was sitting at the computer. Was that after the bear arrived?
I'm here. No.
That's true, it wasn't that fast enough.
Yes.
Any pictures of your batteries?
I will look. I don't have any in the presentation.
How do you test your battery? Do you ever test for pH or what's that called? Density?
Yeah, I know what you're talking about. The batteries, some batteries require that. I have a type of battery called an absorbed glass mat battery that's sealed. The electrolyte is actually absorbed in a glass mat, and that was the advantage, lower maintenance for that battery. I also have a device called a battery monitor, which is basically a voltmeter and an ammeter measuring the charge state of the battery, and it also gives me an indication of the health of the batteries. So at any given time, I have a meter on the wall that gives me voltage, current, power, historical data about that, and an estimate of percent full of the battery. Yes?
2 questions. Do you have to do anything day to day to turn the system on or off between day and night? Or
No.
It's automatic. Doesn't.
So the charge controller takes care of that?
Yes, that's one of the great things about solar power. I don't have to stop and take a generator out and plug it in and put fuel in it and turn it on. Whenever there's sun out, the charge controller turns on and starts
Even
charging.
when you're mobile, you continually charge the system.
Yes.
If you park under your street lamp at night,
I haven't tried that, but there is a certain minimum before the charge controller will turn on. I would expect that the street light wouldn't meet that minimum. Yes?
How much area does solar panels does your system take to run a 2C?
I have 600 watts of solar power, but I'm planning for much more than just the 2C.
Okay.
So I
600. How many square meters?
I don't know the dimensions offhand. I can show you the picture that was in the beginning, but I don't offhand have the dimensions.
And the solar array, you don't have to do anything to it to become mobile. You don't have to put anything away or redo anything. It's fixed at that angle full
Mhm.
time.
It is fixed, yes. As I pointed out earlier, I would get more solar power if I could tilt the panels, but that requires a lot more interaction on my part, so anytime I close the door and drive away, and my solar power keeps working.
you park on a slope.
I could, yeah.
It affects the angle of it affects the angle to which the light hits
Mhm.
But pouring the coffee is a little tougher.
yeah.
Get out the jack and let them say.
Mhm.
Park downhill to the south?
Yeah, that's a good point. that would help. I'd make my coffee beforehand, but yes.
Did you do any research on figuring out alternative sources of putting power in? I was thinking of see, you've got a couple bikes on the back, putting up a little roller and, you know, running a motor to act as an alternator to generate power. Any idea how much power you can generate in a realistic manner?
I don't
Something
know.
like that?
I thought briefly about that, and that seemed like more work than I wanted to put in to
Right.
generate power, so I didn't research how much power it could generate. But yeah, that's another great idea.
Humans
generate in the low two digits of wattage.
I was gonna
Is
say,
that what it is?
Got it.
From the various science, I can remember a couple of different ones, and I remember lighting a 75-watt bulb is about as far as you get. And that's going pretty good.
That's
And it wears you out.
Yeah, I was gonna say, the athletes among us might be able to do 100. You know.
So much time to relax and stop.
Where I can't.
Yeah.
Well, back in the late 80s, I got involved with a program that was sending Apple II computers over to Africa in the backcountry, and they had decided on Apple II's #1. The church that was involved, their people that were going over there were experienced Apple II users, and they were running solar, and I never heard what their auxiliary source was. And I don't know whether it's bicycles. I've seen pictures of people that are using kids' merry-go-round playgrounds, the rotation value of that. For pumping water, maybe they were doing that to generate power as well, I don't know. But they kept that program going for 6 or 7 years at least. I don't know whether it's still going on. I would imagine they upgraded the system, but we were getting donated machines. My club was refurbishing the machines to make sure that they were all in good shape. Put them in a shipping container with all the other stuff they need, and every time they'd exchange staff, they'd send off a shipping container and use them in the schools.
What kind of software
Interesting.
do we use?
What?
What kind of software?
We sent them with AppleWorks. We got a grant from Apple to use AppleWorks. There were some games. Some of the stuff was donated. I think some of them they had written grants and gotten donations from the various companies, because we're not talking about a large number of units.
Do they do any printing?
I don't remember the details. I'm sure they must have, but I would imagine it was a
Low-tech system?
well, it was a low amount of printing because they didn't have the money to buy the paper and the supplies for printing. They were using the computers mainly as a, way to just get into computing. They definitely weren't doing wireless or any of that technology. But again, that was late 80s. And over 25 years, technology has changed. So they may very well have laptop computers and wireless, and the same solar system that they were using then is probably still working, but they're again using the efficiency of a laptop, so now they can probably run laser printers and all sorts of stuff. But I just haven't kept up with that project. But it was really fun, hearing the presentation and then renovating the machines to send overseas, stuff that would have been otherwise probably junk.
Thank you for sharing. It's a good story.
Peter.